I am James Snell. I am the head of research for NearForm research. I just want to say something just really quick about this because I'm actually quite excited about this. NearForm research is a new group we launched within NearForm to really develop a proper research and development capability. We're a services company, but we also have always done a lot of kind of leading edge work and open source and that kind of thing. But what's different about NearForm research is we're not looking at just developing proprietary intellectual property for NearForm. The idea is to develop technologies and capabilities for the entire ecosystem. So everything that we're doing is focusing on open source. Everything that we're doing is focusing on new capabilities, new features for the entire platform. And QUIC is one of the things that we are working on, adding to Node, not just for us to use, but for everybody to use, right? So this is something you're really excited about. The one last thing I will say about this, and this goes back to the talk Kian gave this morning. Think about, if you are working for a company that is generating value, getting value from open source, I want you to stop and think about how much of that value is making its way back to the maintainers and the original authors of the open source packages you're developing. Typically, that's very, very little, right? So we all need to start collectively thinking about how do we start getting some of that value back to those maintainers, all right? Very, very important thing. All right, so let's talk about QUIC, and really specifically HP3. We're gonna do a quick recap. We just added HP2 to Node. I think we landed it in 2017. My youngest son, he's taught himself like 4 programming languages in the past 2 years. He's just like me, just a big nerd. And he knows what I work on with Node. And I was working on the couch one day, and he comes out and says, so hey, what are you working on? I said, HP3. And he's kind of stopped. Didn't you just finish HP2? Well, yeah. He kind of shook his head and walked away. So HP3, it's a thing. It's out there. We're working on it. But let's talk about it a little bit. HP2, we got it into Node. It's got a familiar API. We got multiplexing, we got push streams, we got flow control. We got all these things that are these great features of HP2. Unfortunately, it's not very usable. And there's a few reasons why it's not very usable. And those reasons are exactly why we want to push HP3 fairly quickly. All right, so the first one is, we can talk HP2 from one Node instance to another Node instance. You can talk HP2 from a browser to Nginx. But unless you're using gRPC, you cannot talk HP2 from Nginx back to a Node server, or pretty much from almost any of these middle boxes, right? Very few of the middle boxes actually support HP2 back to the end and don't intend to, right? It just will not ever happen. And the reason, there's several reasons, but the main one is that HP2 becomes a stateful protocol. So if you think about HP1, you send a message, it's got the headers, right? You get the response back. There's no state that has to be maintained at that middle box layer, right? They just take the message and route it right along. With HP2, however, they purposefully switched the protocol to where it maintains state, and it's in one very specific place, and that is with headers. The headers themselves, if you think about a message when it's going back and forth, there's a tremendous amount of data, whether you're talking about the user agent string or the date strings or your authentication or whatever else. There's a huge amount of data that's passed back and forth with every message. With HP2, they had the idea, hey, let's reduce the amount of data that needs to go, so they introduced a header compression scheme. Well, the scheme that they used is a delta encoding. The delta encoding basically means that they're gonna send the data once, and then the next message on the same connection, they're gonna say, I'm gonna reuse the data I sent before, or I'm only gonna send the data that's changed. So in order to be able to do that, you have to maintain state from one request to the next over that connection. Unfortunately, with HP2, because of how the protocol is defined, all of the middle boxes have to terminate that state and maintain that state at every hop. So there's a significant amount of additional resource that is required at those middle box layers in order to be able to support HP2. So because of that, and because of some other reasons, they don't really want to support that going back. They'll support it terminating from the browser, right, and then talk HP1 back to the back end. So even though we added HP2 in Node, it's kind of not useful, right? It was a good exercise to go through and do. There are use cases for it. If you're talking from one Node server to another Node server, for instance, on the same backplane, it works really well. But if you have to put an Nginx in front of it, it's not going to work very well. There's a more significant problem, though, and that is TCP head-of-line blocking. All right? So the way that this works is fairly simple. With HP1, you send one request and response over the wire at a time, right? Since we're using TCP, you take that message, you divide it up into a sequence of TCP packets, and those are sent. TCP is a strictly ordered sequence of packets. You send, one, you send a stream of them. If the one at the head of the line, if it's lost, if it's dropped, if it's corrupted in any way, if it's not received properly, all the other packets wait until that one is sent successfully, all right? So everything ends up getting blocked. Now with HP1, if that happens, you're only blocking one request, right? With HP2, however, we have the concept of multiplexing, where you can put multiple requests, multiple responses in flight at the same time over a single TCP connection. Now what happens if a single packet drops? How many connections are being blocked? Or how many requests? All of them, right? So you end up with this compounding problem of if you drop a single TCP packet, you end up blocking a lot more traffic than you would if you just had a single HP1 connection, all right? Multiplexing was originally intended to stop head-of-line blocking within HP. And the issue is it did stop it at the HTTP level, but it made it worse at the TCP level. And if you're talking about connections that are long distance, high latency, or low reliability, you end up with a significant performance issue that just kind of compounds in on itself, all right? Now, there are ways around this, but for the most part, this is one of the flaws with HP2 in general. HP3 and QUIC specifically look at fixing this particular problem, all right? So we don't want to just forget about HP2, but it will be limited, all right? So let's switch. Let's talk about QUIC. QUIC is a new UDP-based transport protocol for HTTP, and not just HTTP, but we'll talk about in a bit other protocols as well. It's the old thing. You can, tell you a UDP joke, you're not going to get it, right? UDP is unreliable, right? It's got flow control issues. You can send 100 UDP packets. You have no idea what order they arrived or if any of them arrived or anything else, right? So why the hell would we build a protocol on top of UDP, right? The issue, or the thing that we're building on here, is that UDP packets are completely independent of one another. You can send them, all right? You can send them in any order. You receive them in any order, you can retransmit them or whatever, but if one gets dropped, you just keep sending the others, and you can just retransmit the one that gets dropped, right? Now that introduces a few other issues, like, how do you actually keep track of which ones got dropped, and how do you actually build some reliability into this? So this is what QUIC does. QUIC adds error handling, acknowledgements, flow control, packet sequencing, built-in encryption, bidirectional and unidirectional streams to UDP. So it takes all the stuff that TCP gives you and just layers it on top of UDP. Now, on the network, it still just looks like UDP traffic, right? So you can still route it just like UDP packets. You can forward them along. All the addressing information is still in there. But we're layering in additional pieces of information, such as a sequence number. Every packet is given a number. So when you start sending these things out, if you drop packet 2, you can keep sending all the other packets, but then just retransmit packet 2. Every packet is acknowledged, right? So you receive it, you send an acknowledgement. If you don't receive an acknowledgement within a certain period of time, you assume it's lost, you retransmit it. There's flow control, right? UDP is famous for being able to just flood a network, right? It's something, it's a lot of problems. With QUIC, you can actually see significantly higher bandwidth usage on a network because of all the acknowledgements and the retransmissions that are happening. But the flow control gives us a way of bounding that. In theory, with QUIC, you could send an entire stream of information in a completely random order or reverse order, right? And your buffering requirements on the receiving end would just blow up. So with flow control, you can only send within a certain window, right? So only send me this much data at a time, right? Okay, I've acknowledged that, send me a little bit more. So QUIC adds that on top of UDP. The built-in encryption, this is a massive one. So instead of TCP and then TLS and then HP, that layering, TLS 1.3 is baked into QUIC. You cannot separate it. You cannot use QUIC without using TLS. The handshake is built into the establishment of the QUIC session. Every single packet that's sent is encrypted. Now it's different layers, right? You have the initial handshake and then everything after that. Once it establishes the secrets, there's multiple layers of encryption that happen. Now here's the fun thing. If you are on a TCP connection, say on your phone on Wi-Fi, right, and you're watching a video, what happens when you lose Wi-Fi and switch to LTE? The transmission dies, right? That's because that TCP connection is tied to your IP address. With QUIC, it's not. You can actually establish a QUIC connection, go through the entire TLS handshake, and then switch your network without having to re-handshake. It maintains the secrets, maintains all of the information. You'll see a slight loss, some packet loss as it works to reestablish the path, the network path that it's going to be sending those things on. But the connection itself won't drop, and you won't have to re-handshake. So QUIC adds a lot of these things in on top of UDP. So it takes the unreliability of UDP and then resolves those issues with QUIC. All right, so what does this look like in Node? We've been working for a while on getting this implemented, and the majority of the effort that we've been putting into this has been making the API as familiar and simple as possible. This is still very, very experimental, still very much under development, so this is not code you could use in production in any way. It's more likely to segfault on you than anything else. But we create a socket, and this is a local UDP socket. It can be used as both a client and a server simultaneously. Here we're setting up a server. We're telling it to listen, port 443. We specify the TLS key cert CA information, and then we just tell it to wait for a session to be created. Once a session is created, we're going to wait for a stream to be created, and then we can respond to it. This stream, it's a QUIC stream object. It's essentially just a duplex. You can read data from it, you can write data to it. Right? If you're familiar with the Node API already, there's nothing here that should be surprising in any way. Creating a client, equally straightforward. Instead of listening, you're going to connect. You get this rec, it's actually a session object. The on-secure is when the TLS handshake is done. At that point, you can create a stream, write to it, and you're done. Now, QUIC is just a transport protocol. The way that we've implemented this, we can do HTTP3 on top of this, and there's going to be another API layer on top of this that does HTTP3. But with the way that we've implemented this, you can use QUIC to implement your own protocols however you want. All right? You can specify your own ALPN, which is the TLS mechanism for identifying what protocol you're writing. You can have whatever data format you want. It's just a channel for transporting the data back and forth. And we handle all of the QUIC protocol details while you can handle your own application on top of it. And HTTP3 is just an application on top of QUIC. All right, so QUIC does not equal HTTP3. You'll see these used interchangeably quite a bit, but they are not the same thing. All right, the layering is fairly simple. Before, where we had IP, then TCP, then TLS, and then HTTP, here QUIC replaces the most of the TCP and the TLS layer. Right? So it's just there. That HTTP3, you can take that out and use it for, replace it with whatever you want. Within Node, we're likely to have a couple of different protocols, not just HTTP3. I'm working on, just for instance, I'm working on a version of the inspector protocol that instead of using WebSockets, we'll use QUIC. There's also, just some other diagnostic kind of things that I'm looking at and kind of playing around with, just as a making sure we can do it, right, kind of thing. So we'll see, it's going to take a while for that stuff to get done, but we will have multiple uses of this, not just with HP3. All right, so let's see here. Oh, it looks like this thing's dead. All right, so progress. I want to, first of all, Tatsuhiro-san is the author of NGTCP2. He's also the author of the NG-HP2 library that we use for HP2. This is an absolutely phenomenal developer out of Japan, just absolutely amazing. I absolutely, love his code. Love the work that he does on this. We're relying very heavily on this library, and I hope he sees the video of this, so I can I'm thanking him for the work that he's done. Work is underway. I'm expecting the experimental PR, the initial PR, to be open by the end of this month on Node Core. We're doing it in a separate repo right now, and I'm hoping to merge the stream into Node Core very soon. But it'll still be experimental, probably at least for the next year. We really want to make sure we get this API correct. And there's more than just the API. There's additional capabilities that we're adding in here that don't currently exist in other network protocols within Node. For instance, I'm building in the ability to do performance metrics directly into the API. So we'll be able to monitor the data flow, data throughput. We'll be able to monitor basically, like, how long is the handshake taking? How long is the data flow taking? So you can actually actively respond to slow clients, and particularly security situations. If you have a malicious client or malicious server that is taking too long to actually respond to things and making you keep your resources alive for too long, you'll actually be able to actively detect those and respond to them from within Node without having to have any additional software installed. We will have the ability to at least detect those things built in. And there's some other performance monitoring and things that we want to do there as well. I don't know if you're familiar, if you've looked at HP2, earlier this year there was this massive security issue with HP2. That was basically every single implementation of HP2 out there suffered from the same set of denial of service attack issues. And I kind of want to make sure we don't have the same problem with HP3. So I don't want to rush it out of experimental until we're sure that that things are hardened and that stuff is done. Work is being sponsored. I have to thank Protocol Labs. They really helped kind of kick off this effort. NearForm's covering a significant chunk of this as well. But it is open source. We're doing all this work out in the open, and we absolutely would love help. So come take a look at it and stuff like that. I wanted to leave a little bit of time to show the demo. It's not going to be much. You're going to see a bunch of text fly across the screen. But basically, this is one of our tests. I have, is it actually going to come up? Probably not. Hold on a second. I think I have to stop presenting. There we go. So this is one of our tests that we're using, and I have debug tracing enabled. Basically, you're just going to see a bunch of text fly across the screen, but it's a client talking to the server, sending a copy of the test file itself back and forth. All right? But I want to, once it's through, I want to point out a few things that we see in the results. So this is, sending all the UDP packets. This is all the trace information. It'll take just a second here. But it actually works, which I'm super happy about because last week this was seg faulting like crazy. All right. So we see here at the end when in these objects, and all this information is available to the JavaScript layer. But we have here, you can see the bytes sent, right? You can see the number of streams that were created. If you scroll up here a little bit further, we'll see that, how many bytes were received on a particular session, when the handshake started, when it completed. This is all information that's going to be available at the JavaScript API layer just built in here. So right now, this is information that you would have to install additional modules to get in other things within Node. This is all going to be built into the API and available. So that's nice. One of the other things we can do here, there's key logging support. So because we have TLS in here, you can enable key logging support, and you can use Wireshark to do real-time traces of the traffic going back and forth. And that's about it. So that's where we're at with QUIC so far. It's come a long way. I have to thank Anna. I think, I'm not sure if she's in here. She's back over there. I add the bugs, she fixes them. Which, yeah. So thank you, and that's it. Thanks a lot.